The Mariana Trench is the deepest place on Earth, a yawning chasm in the Pacific Ocean floor that plunges nearly 7 miles below. The surface. If you dropped Mount Everest into its depths, the peak would still lie more than a mile underwater. For most of human history, this abyss remained completely unknown. We mapped the surface of Mars before we explored the bottom of our own ocean. And when we finally descended into that darkness, what we found changed everything we thought we knew about life, geology, and the limits of survival. This is not empty water. This is not a lifeless void. The Mariana Trench is teeming with strange creatures, bizarre geological features, and phenomena that defy easy explanation. Scientists have recorded sounds down there that shouldn't exist. They've found plastic pollution in organisms, living at crushing pressures that would flatten a submarine. They've discovered entire ecosystems thriving in conditions that would instantly kill almost anything from the surface world. The trench is not just deep, it's alien, a window into processes that shaped our planet billions of years ago and continue today. Every expedition reveals something unexpected. Every descent raises more questions than it answers. So what exactly lies at the bottom of the deepest place on Earth? Let's descend into the darkness, find out. The geography of the abyss. The Mariana Trench stretches across the western Pacific Ocean, approximately 1,580 miles long and 43 miles wide on average. This immense scar in the seafloor runs in a crescent shape east of the Mariana Islands, from which it takes its name. The trench formed at the boundary between two tectonic plates, the Pacific Plate, the smaller Philippine Sea Plate, where these massive sections of Earth's crust meet. One slides beneath the other in a process called subduction. The Pacific Plate, being denser and older, dives downward beneath the Philippine Plate at a rate of about 2 to 3 inches per year. This might sound slow, but over millions of years, it has created the deepest ocean trench on the planet. The trench's deepest point is called Challenger Deep, named after the HMS Challenger, the British survey vessel that first measured the trench's depth in 1875 using weighted sounding ropes. Modern measurements place Challenger Deep at approximately 36,037 feet below sea level, though different expeditions have recorded slightly varying depths due to the difficulty of precise measurement at such extreme distances. To put this in perspective, commercial airliners cruise at about 35,000 feet above sea level. The bottom of Challenger Deep sits farther below the ocean surface than jets fly above it. The trench doesn't maintain a consistent depth along its length. Instead, it features a complex topography of ridges, valleys, and steep slopes. Some sections are relatively shallow, only 4 or 5 miles deep, while others plunge past 6 miles. The southern end of the trench, where Challenger Deep lies, represents the absolute maximum depth. The walls of the trench are not vertical cliffs, but rather steep slopes, typically angled between 8 and 15 degrees. This might not sound dramatic, but over miles of descent, these slopes create nearly sheer underwater mountains. The geological process creating the trench continues today. As the Pacific Plate subducts beneath the Philippine Plate, it carries with it sediments from the ocean floor, layers of clay, dead, organisms, and mineral deposits accumulated over millions of years. Some of this material gets scraped off and added to the edge of the overriding plate, forming what geologists call an accretionary wedge. The rest gets pulled down into Earth's mantle, where extreme heat and pressure eventually melt it back into the planet's interior. This recycling of oceanic crust is a fundamental part of plate tectonics, the system that drives continental drift, volcanic activity, and earthquakes. Around the trench's edges, volcanic activity manifests in several ways. The Mariana Islands themselves are volcanic, formed by magma, rising through the overriding plate as water released from the subducting slab lowers the melting point of surrounding rock. This creates a volcanic arc parallel to the trench, a common feature at subduction zones worldwide. Underwater volcanoes dot the region, some active, others dormant for millions of years. These volcanic features interact with the trench system, creating additional complexity in the seafloor topography. The trench also exhibits what geologists call back arc spreading. Behind the volcanic arc, the crust actually pulls apart, allowing new oceanic crust to form. This creates a smaller basin called the Mariana Trough, effectively making the region a site of both crust destruction in the trench and crust creation in the trough. Few places on Earth demonstrate such dynamic geological activity in such close proximity. The interplay between these processes has shaped the entire region's structure over the past 50 million years. Sediment distribution in the trench follows unusual patterns. The deepest parts accumulate relatively little sediment because the steep slopes cause most material to slide down into shallower areas or get carried away by deep ocean currents. What does accumulate consists primarily of extremely fine clay particles and the microscopic shells of dead plankton that drifted down from surface waters over thousands of years. Core samples from a trench floor revealed distinct layers corresponding to different geological periods, providing a timeline of ocean conditions stretching back millions of years. The trench's isolation creates unique conditions. Deep ocean. Currents largely bypass the deepest sections, creating relatively stable water conditions compared to shallower depths. Temperature at the bottom remains constant, at just above freezing, around 34 to 39 degrees Fahrenheit. This consistency has lasted for millions of years, creating an environment that changes only on geological timescales. Organisms adapted to these conditions have evolved in a stable, if harsh, environment, very different from the dynamic surface world. Hydrostatic pressure at Challenger Deep reaches approximately 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This pressure would instantly crush any air-filled cavity, compressing gases to tiny fractions of their surface volume. The pressure differential between the trench floor and surface represents one of the most extreme environmental gradients on Earth, comparable to the difference between sea level and the edge of space. Yet life exists at both extremes, demonstrating biology's remarkable adaptability. The trench's position in the Pacific also affects its characteristics. The Pacific Ocean contains the oldest oceanic crust on Earth. Some sections date back 200 million years. This ancient crust is cold, dense, and heavy, making it particularly prone to subduction. The Pacific Plate's movement drives not just the Mariana Trench, but also similar trenches around the Pacific Rim, creating the ring of fire of volcanic and seismic activity that characterizes the entire Pacific Basin. The Mariana Trench represents the deepest expression of processes occurring all around the Pacific's edges. The descent through ocean zones. Understanding what makes the Mariana Trench special requires understanding the ocean's vertical structure. Scientists divide to the ocean into distinct zones based on depth, each with characteristic conditions that determine what life can exist. There, the journey from surface to trench floor passes through of these zones, each more extreme than the last. The sunlight zone, or epipelagic zone, extends from the surface to about 660 feet deep. This is where most familiar ocean life exists. Sunlight penetrates sufficiently for photosynthesis, supporting phytoplankton that forms the base of marine food webs. Temperatures range from tropical warmth to frigid polar cold, depending on latitude. Most commercial fishing targets species in this zone. Pressure remains low enough that humans can dive here with basic equipment. This zone represents less than 5% of the ocean's total volume, but contains the vast majority of its biomass. Below lies the twilight zone, or mesopelagic, extending from 660 to 3,300 feet. Sunlight becomes progressively dimmer, fading to complete darkness at the bottom. No plants can grow. Here, insufficient light for photosynthesis. Temperature drops rapidly with depth, creating a thermocline that acts as a barrier between surface and deep waters. Many fish species live here, most featuring specialized adaptations like large eyes to capture minimal available light or bioluminescence to produce their own light. The mesopelagic contains the ocean's largest animal, migration. Each night, billions of small fish and zooplankton rise into the sunlight zone to feed, descending again before dawn. The midnight zone, or bathypelagic, runs from 3,300 to 13,100 feet. Total darkness prevails. Pressure reaches 5,900 pounds per square inch, enough to crush most surface organisms. The temperature hovers just above freezing. Food becomes scarce. Only organic debris drifting down from above sustains life here. Creatures of the bathypelagic have evolved remarkable adaptations. Many have huge mouths and expandable stomachs to consume prey, larger than themselves, crucial when meals are rare. Bioluminescence becomes more common, used for hunting, communication, and defense. Some species have light-producing organs that dangle in front of their mouths like fishing lures, attracting prey close enough to strike. The abyssal zone spans 13,100 to 19,700 feet. At these depths, pressure exceeds 8,000 pounds per square inch. The seafloor here consists of vast, flat, abyssal plains covered in fine sediment. Until recently, scientists assumed this zone was a biological desert, too cold dark, and pressurized to support much life. Modern exploration has proven this assumption spectacularly wrong. The abyssal plains host diverse communities of organisms, see cucumbers, brittle stars, amphipods, and various worms feeding on the constant rain of organic matter from above. Some regions feature higher densities of life than others, depending on nutrient availability and water circulation patterns. Finally comes the Hadal zone, named after Hades, the Greek underworld. This zone encompasses all ocean depths below 19,700 feet, existing only in the deep ocean trenches. The Hadal zone is not a uniform environment, but a series of isolated habitats each. Trench represents a separate ecosystem, often with unique species, found nowhere else. The Mariana Trench contains the deepest hadal environment on Earth, plunging past 36,000 feet at Challenger. Deep. Descending through these zones, pressure increases by approximately 1 atmosphere for every 33 feet of depth. At Challenger Deep, the pressure reaches 1,086 atmospheres. A human body at that depth would experience 16,000 pounds of force on every square inch of skin. Air-filled spaces would compress to nearly nothing. The pressure is sufficient to compress water itself by about 5% compared to surface water, making the trench's water slightly denser than normal seawater. Temperature changes follow a complex pattern during descent. Surface waters might be warm, but temperature drops rapidly through the thermocline, reaching near freezing temperatures below 3,000 feet. In most of the deep ocean, temperature remains constant at around 36 degrees Fahrenheit. However, in the Mariana Trench, hydrothermal activity creates local temperature variations. Some vents spew water heated to several hundred degrees, while surrounding water remains near freezing. This creates extreme temperature gradients over very short distances. Light disappears completely by 3,000 feet in clear water, potentially shallower in murky conditions. The trench floor exists in absolute darkness, has for millions of years, and will remain dark until continental drift eventually closes the trench in the distant geological future. The only light sources are bioluminescent organisms, occasional volcanic vents glowing dull red from heat, and the artificial lights of research submersibles. This eternal night has profound implications for evolution. Eyes become useless, other senses dominate. Oxygen levels decline with depth in most oceans due to lack of photosynthesis and consumption by bacteria decomposing sinking organic matter. Some ocean regions develop oxygen minimum zones, where oxygen becomes so depleted that only specialized organisms survive. However, cold bottom currents originating in polar regions carry oxygen-rich water into the deep ocean, including trenches. The Mariana Trench's water contains sufficient dissolved oxygen to support animal life, one factor enabling the surprisingly diverse ecosystem found there. Salinity remains relatively constant throughout the ocean's depth, approximately 35 parts per thousand in most locations. However, local variations occur. Hydrothermal vents add dissolved minerals, temporarily increasing salinity in their immediate vicinity areas. With high evaporation at the surface, can create slightly saltier water that sinks. The trench's bottom water shows subtle chemical signatures reflecting its origin in distant polar regions where dense, cold, salty water formed and began its centuries-long journey along the ocean floor. Each zone presents escalating challenges to life. Surface: organisms face predation, competition for resources, and environmental variability. Deep-sea creatures face crushing pressure, eternal darkness, near-freezing temperatures, and extreme food scarcity. Yet life persists at every depth, adapted to conditions that would instantly kill organisms from other zones. A fish from the sunlight zone brought to the trench floor would be crushed and frozen. A trench organism brought to the surface would literally fall apart as gases dissolved in its tissues at high pressure expand catastrophically, a phenomenon called explosive decompression, the first human descent. On the 23rd of January 1960, two men climbed into a spherical steel chamber barely large enough to hold them both. The chamber, called a bathyscaphe, hung beneath a large float filled with gasoline, chosen because gasoline is lighter than water and incompressible, providing buoyancy without collapse under pressure. The men were U.S. Navy Lieutenant Don Walsh and Swiss oceanographer Jacques Piccard. Their destination was the bottom of Challenger Deep, the deepest point in Earth's oceans. No human had ever attempted such a dive. Most scientists doubted anyone could to survive the journey. The bathyscaphe was named Trieste, after the Italian city where it had been constructed. The design consisted of a crewsphere 7 feet in diameter with steel walls 5 inches thick, suspended beneath a much larger float tank measuring 59 feet long. The float tank held 28,800 gallons of gasoline for buoyancy and 16 tons of iron pellets as ballast. To descend, the crew flooded ballast tanks with seawater, making the craft heavy enough to sink. To ascend, they released the iron pellets, becoming light enough to rise. No. Engines powered the descent or ascent. The craft simply sank and rose like a submarine elevator. The dive began at 8:23 a.m. Trieste dropped slowly at first, then faster as it passed through the thermocline, where water density changed. Piccard and Walsh monitored instruments packed into the tiny sphere. Small windows, cone-shaped, with the narrow end facing outward, allowed them to see into the surrounding water. The windows were made of plexiglass, 7 inches thick at the outer face, carefully calculated to withstand the pressure. At 300 feet deep, they heard a loud crack. Something had broken. They couldn't determine what, but the instruments showed no immediate danger. They decided to continue. The crack, they later discovered, came from a plexiglass window in the entrance tube. Not structural, not life-threatening, but alarming nonetheless. Unknown failures at extreme depth could prove fatal, yet turning back meant months or years before another attempt. They descended into darkness. By 2,000 feet, all natural light had vanished. They switched on external lights, illuminating a snowstorm of marine snow, dead plankton, fecal pellets, and other organic debris constantly drifting downward, feeding deep-sea life. Schools of small fish appeared in the lights, then vanished. At 18,000 feet, they passed. The deepest point humans had previously reached. Everything beyond was unexplored territory. The temperature inside the sphere dropped steadily, despite the men's body heat in the confined space. Condensation formed on the cold steel walls. They wore heavy clothing to combat the chill. The descent rate varied with depth, faster in some zones, slower in others, depending on water density and the ballast configuration. They couldn't rush. Dropping too fast risked losing control. The iron ballast was their only means of ascent. Once released, couldn't be recovered. At 27,000 feet, they entered the Hadal zone. No human eye had ever witnessed this realm. The pressure outside exceeded 12,000 pounds per square inch. If the sphere failed, implosion would occur in milliseconds, faster than human nerves could register pain. They would simply cease to exist. The steel groaned occasionally as it flexed under the load. Normal sounds, Picard assured Walsh, though neither could be certain. At 32,000 feet, they slowed the descent, carefully releasing ballast to control their speed. The echo sounder showed the bottom approaching. At 35,797 feet, measurements would later be refined to 35,814 feet. Trieste touched bottom. The time was 1:06 p.m, nearly 5 hours after departure from the surface. They had reached the deepest point on Earth. The bottom was not empty. Peering through the viewport, Picard observed what he later described as a flatfish, about a foot long, lying on the seafloor. This sighting, though later questioned by some scientists who doubted fish could survive such depths, proved that higher life forms existed even here. Walsh confirmed seeing the organism, noting it resembled a flounder or sole. Whether truly a fish or some other bottom-dwelling creature, its presence demonstrated that the deep trenches were not sterile voids. They remained on the bottom for 20 minutes, photographing through the viewport and making observations. The sediment appeared light-coloured, possibly cream or tan, disturbed slightly by their landing. No other life was visible in the limited area illuminated by their lights. The water was clear, clearer than they'd encountered at shallower depths. The pressure gauge read 16,883 pounds per square inch. The temperature was 37.4 degrees Fahrenheit. Then they began the ascent. Releasing iron ballast, Trieste rose, slowly at first, then faster as it climbed through zones of different density. The trip took 3 hours and 27 minutes. They surfaced at 4:56 p.m. to find their support ship waiting. The dive had taken more than 8 hours total. Both men were cold, stiff from confinement but unharmed. They had proven that humans could reach the ocean's deepest point and return alive. The Trieste dive remains one of the most significant achievements in ocean exploration. For decades afterward, no one repeated the journey. The technology was dangerous, expensive, and the scientific community debated whether the risks justified sending humans instead of robots. It wasn't until 20125, 2 years later, that filmmaker James Cameron made the next solo descent to Challenger, deep in a specially designed submersible called Deep Sea Challenger. His dive lasted about 3 hours on the bottom, considerably longer than Trieste's brief visit, allowing more extensive filming and sample collection. Crushing pressure and its effects. The pressure at the bottom of the Mariana Trench is difficult to comprehend. Numbers alone don't capture reality. At Challenger Deep, every square inch of surface experiences a force of approximately 16,000 pounds more than 1,000 times the pressure at sea level. To visualize, imagine 50 jumbo jets stacked on top of to your thumbnail. That's roughly the force concentrated on that tiny area at the trench floor. This pressure exists on every exposed surface simultaneously, from every direction at once. Pressure in fluids works differently than on land. A book sitting on a table experiences pressure from above the weight of air above it, about 14.7 pounds per square inch at sea level. But in water, pressure comes from all directions equally. At depth, water pushes on an object from the sides, top, and bottom with equal force. This omnidirectional pressure is why submarines must be built as spheres or cylinders, shapes that distribute force evenly across their surface. Water itself is nearly incompressible, meaning it resists being squeezed into smaller volumes. This property explains why pressure increases so dramatically with depth. The water at the bottom of the ocean has nowhere to compress to. Instead, it pushes with immense force against anything in contact with it. The water column above weighs enormous amounts. At Challenger Deep, every square centimetre supports the weight of a 36,000-foot column of seawater. That's why pressure is sometimes measured in atmospheres. 1 atmosphere equals the pressure at sea level. So, Challenger Deep experiences about 1,086 atmospheres of pressure. This pressure affects everything. Air-filled objects collapse instantly at trench depths. A foam coffee cup taken down in a submersible sample basket returns compressed to the size of a thimble, its original structure crushed beyond recognition. Styrofoam, full of tiny air bubbles, compresses to a fraction of its original volume, becoming dense and hard. Wooden objects shrink as the air in their cellular structure gets compressed. Even steel deforms under such pressure if not properly designed to withstand it. Submarines designed for moderate depths cannot approach the trench. Military submarines typically operate at maximum depths of 1,500 to 2,500 feet, some specialized ones reaching 3,000 feet. The pressure at those depths, though substantial, is only a fraction of what exists at the trench floor. A submarine designed for 3,000 feet would implode catastrophically if taken to 30,000 feet. The water would rush inward faster than the human eye could follow, crushing everything inside to fragments in milliseconds. Specialized submersibles built for extreme depths employ thick steel or titanium spheres for crew compartments. The Trieste's crew sphere had 5-inch thick steel walls. Modern designs use titanium, which is stronger relative to its weight, allowing slightly lighter construction. But even titanium must be several inches thick for depths exceeding 20,000 feet. The sphere shape is crucial. It distributes pressure evenly, preventing concentration of force that could initiate failure. Any protrusion, any unevenness in the wall thickness becomes a potential failure. Point: the viewports present special challenges. Glass or plexiglass must be extremely thick, often 7 to 10 inches for trench depth vehicles. The ports are conical, wider on the inside than outside, so pressure pushes the viewport into the hull rather than out. Despite these precautions, viewports remain the weakest points. Several deep diving vehicles have experienced viewport failures, though fortunately at test depths rather than with crew aboard. The consequences of failure at maximum depth would be instantly fatal. Pressure affects human bodies in complex ways. Our bodies are mostly water, which is incompressible, so we wouldn't be crushed to pulp immediately like air-filled objects. However, we have air, spaces, lungs, sinuses, middle ears. At trench depth, these would compress to nearly nothing. The air in your lungs would occupy roughly 1/1000th of its surface volume. Breathing would be impossible. The lungs would collapse completely. But there's more. Gases dissolve in liquids under pressure more. Pressure means more dissolved gas. At great depth, breathing air would force massive amounts of nitrogen and oxygen to dissolve in blood and tissues. This causes nitrogen narcosis at moderate depths, creating an effect similar to alcohol intoxication. At greater depths, oxygen becomes toxic. At trench depths, the pressure would dissolve so much gas in body tissues that bringing a person back to the surface would cause gases to fizz out of solution like opening a shaken soda bottle. This would tear tissues apart from the inside. Deep-sea fish avoid these problems because they don't have air-filled swim bladders like shallow water fish. Instead, they have oil-filled livers or other tissues that provide buoyancy without compressible gas. Their cellular structure has adapted to high pressure. Proteins fold differently under pressure, and trench organisms have evolved protein variants that function normally under conditions that would denature surface organisms' proteins. Some deep-sea bacteria require high pressure to survive. They cannot live at surface pressure, which for them is lethally low. When deep-sea organisms are brought to the surface, decompression can kill them. Fish from moderate depths have swim bladders that expand as they rise, sometimes protruding from their mouths or rupturing their stomachs. Organisms from the trench face similar trauma, though their lack of gas-filled spaces means they're more likely to survive the pressure change itself. However, the temperature increase and pressure decrease can still damage their cellular machinery. Many trench animals arrive at the surface dead or dying, making them difficult to study alive. Scientists use specialized collection devices to capture deep-sea organisms and return them to the surface in pressurized containers, maintaining something close to trench pressure during the ascent. Even so, keeping these animals alive requires not just pressure control, but also proper temperature, salinity, and dissolved gas levels. Laboratories studying trench organisms need specialized high-pressure aquariums, expensive and complex, equipment that limits how many institutions can conduct such research. The strange geology of subduction zones. The Mariana Trench exists because of plate tectonics, specifically a process called subduction. Earth's outer shell, the Lithosphere consists of several large plates and many smaller ones, all moving relative to each other at rates of inches per year. Where plates collide, several things can happen depending on the types of crust involved. When two oceanic plates converge, or when an oceanic plate meets a continental plate, the denser plate typically subducts beneath the lighter one, diving into the mantle below. The Pacific Plate, one of Earth's largest tectonic plates, consists of oceanic crust formed millions of years ago at mid-ocean ridges. As this crust moved away from its formation site, it cooled and became denser. Today, the western edge of the Pacific Plate is some of the oldest, coldest, densest oceanic crust on Earth, perfect conditions for subduction. As it collides with the Philippine Sea Plate, it bends downward and plunges into the mantle at an angle of about 10 to 20 degrees near the surface, steepening to as much as 45 degrees at greater depths. This subduction creates the trench itself. Think of it as a crease, where the plate bends downward. The deepest part of the trench forms where the subducting plate curves most sharply before descending into the mantle. The trench's shape reflects the geometry of this bending, not a straight line but a curved arc, matching the curvature of the colliding plate boundaries. Similar trenches form wherever oceanic plates subduct around the Pacific. Ring of Fire, the Japan Trench, the Peru-Chile Trench, the Tonga Trench, all created by the same fundamental process. As the Pacific Plate descends, it carries with it everything on its surface: sediments, seamounts, sometimes even oceanic islands. Some of this material gets scraped off and plastered onto the edge of the overriding plate, forming an accretionary wedge. These wedges can grow over time, adding territory to the overriding plate. Japan, for example, consists partly of material accreted from subducting oceanic plates over millions of years. However, most of the subducting material continues downward into the propacal mantle. At depths of 60 to 120 miles, the subducting slab encounters increasing temperatures and pressures. Water trapped in the oceanic crust, locked in minerals formed when the crust was created, gets released through a process called dehydration. This water rises into the overlying mantle wedge, lowering the melting point of the rock there. Partial melting occurs, producing magma that is less dense than surrounding rock. This magma rises through the overriding plate, eventually erupting at the surface to form volcanic arcs. The Mariana Islands themselves are a volcanic arc created by this process. These islands sit about 100 to 200 miles west of the trench, positioned above the zone where magma is being generated by the subducting slab's released water. The volcanoes are active, though not constantly erupting. Some have erupted historically, others remain dormant but could reactivate. The volcanic chain parallels the trench, maintaining a consistent distance that reflects the depth at which dehydration and melting occur below. Behind the volcanic arc, an even stranger process occurs. The overriding plate is being stretched, creating a back arc basin. In the case of the Mariana system, this basin is called the Mariana Trough. New oceanic crust forms here through seafloor spreading, similar to what happens at mid-ocean ridges. This creates the unusual situation of crust being destroyed at the trench while simultaneously being created behind the arc. Few places on Earth display such a complete range of plate tectonic processes in close proximity. The subducting Pacific plate doesn't simply disappear, seismic. Studies reveal it descending through the mantle, eventually reaching depths of 400 miles or more. At those depths, mineral transformations occur. The minerals in oceanic crust change to denser forms adapted to the extreme pressures. These phase changes can be detected seismically. Earthquake waves travel at different speeds through transformed minerals, allowing geologists to map the subducting slab's path through the mantle. Some seismic evidence suggests subducting slabs can reach the core mantle boundary nearly 1,800 miles below the surface. These ancient slabs, colder and denser than surrounding mantle rock, may accumulate at the bottom of the mantle for billions of years. Others believe slabs get reabsorbed by the mantle at shallower depths. The fate of subducted crust remains a subject of active research and debate among geologists. Earthquakes cluster along subduction zones, making them some of the most seismically active regions on Earth. The Mariana Trench region generates frequent earthquakes as the descending Pacific plate grinds against the overriding Philippine plate. Most earthquakes occur at relatively shallow depths, less than 50 miles, where the plates are in direct contact. Deeper earthquakes, called deep focus earthquakes, can occur along the subducting slab as far down as 400 to 700 miles. These deep earthquakes result from phase changes in minerals rather than brittle fracturing of rock. The 2011 Tohoku earthquake off Japan's coast, which generated a devastating tsunami, occurred at a subduction zone. The magnitude 9 earthquake resulted from sudden movement along the interface between subducting Pacific plate and overriding North American plate. The Mariana region has produced fewer giant earthquakes. Historically, partly because the Pacific plate subducts relatively smoothly here. However, the potential for major earthquakes always exists at subduction zones. A great earthquake at the Mariana Trench could generate tsunamis affecting the entire Pacific basin. Hydrothermal vents and serpentinite mud, volcanoes. Some of the strangest geology in the Mariana Trench occurs at hydrothermal vents, underwater geysers, where superheated water erupts from the seafloor. These vents form when seawater seeps into cracks in the oceanic crust, penetrates downward, gets heated by proximity to magma or hot rock, and then rises back up, dissolving minerals from the surrounding rock. When this hot, mineral-rich water emerges into the near-freezing ocean, the dissolved minerals precipitate out, forming chimneys and creating oases of life in the deep sea. Most famous are black smokers, named for the black smoke they emit, not actual smoke but a cloud of fine mineral particles, primarily sulfides of iron, copper and zinc. The water emerges at temperatures reaching 750 degrees Fahrenheit, hot enough to melt lead. Yet it doesn't boil because the immense pressure at depth raises water's boiling point. The superheated water is acidic and toxic, laden with hydrogen sulfide, methane and heavy metals. No ordinary organism could survive contact with the vent fluid. itself. But at the interface between hot vent water and cold seawater, chemical gradients create opportunities. Bacteria have evolved to harness chemical energy from the vent fluids, performing chemosynthesis instead of photosynthesis. These bacteria oxidize hydrogen sulfide or methane, using the released energy to convert carbon dioxide into organic compounds. They form the base of unique ecosystems surrounding vents, ecosystems completely independent of sunlight. Giant tube worms cluster around black. Smokers, growing up to 8 feet long, they have no mouth, no digestive system. Instead, they harbour sulfur-oxidizing bacteria in specialized organs, forming a symbiosis where the worm provides shelter and the bacteria provide nutrients. White smokers emit cooler fluids, typically below 500 degrees Fahrenheit, and contain different dissolved minerals, primarily barium, calcium, and silicon. These build white or light-coloured chimneys. Some white smokers near the Mariana Trench, particularly in the Back Arc Spreading Centre, emit fluid rich in carbonate minerals. The warm alkaline water supports different bacterial communities than the hot, acidic black smokers. But the Mariana Trench hosts another, even stranger type of vent: serpentinite mud volcanoes. These form through a unique process involving the mineral serpentine when water interacts with certain mantle rocks, particularly peridotite, containing the minerals olivine and pyroxene. A chemical reaction called serpentinization occurs. The water reacts with the rock to form serpentine, releasing heat, hydrogen, gas, and creating a slurry of mud and water. This mud, under pressure, can erupt from the seafloor, forming underwater mud volcanoes. Several serpentinite mud volcanoes have been discovered near the Mariana Trench. The largest, called South Chamorro Seamount, rises about 2,500 feet above the surrounding seafloor at a depth of roughly 13,000 feet. Unlike typical mud volcanoes that are composed of sediment, these serpentinite structures contain rocks from Earth's mantle that have been altered by reaction with water. The mud emerging from these volcanoes is highly alkaline, with a pH around 11 to 12 more alkaline than household bleach. The hydrogen gas produced by serpentinization creates yet another type of chemosynthetic ecosystem. Bacteria here oxidize hydrogen. Instead of hydrogen sulfide generating energy to fix carbon from dissolved carbon dioxide, these microbes can survive in the extremely alkaline environment where most organisms would dissolve. Some scientists hypothesize that similar alkaline vents may have provided the chemical energy needed for the origin of life on early Earth when the surface was still too harsh for photosynthetic organisms. Fluid samples from these serpentinite vents contain dissolved methane and other organic compounds produced by abiotic processes, chemical reactions between water, rock, and carbon dioxide that don't require living organisms. This abiotic synthesis of organic molecules demonstrates that life's building blocks can form through purely geological processes. Understanding these reactions helps scientists model how organic chemistry might emerge on other planets and moons where similar water rock interactions occur. The chimneys surrounding active vents grow steadily as minerals precipitate from the fluids. Some reach heights of 60 feet or more. When a vent shuts off, perhaps because the plumbing system gets blocked or the magma chamber supplying heat cools the chimney, goes dormant, these inactive structures eventually collapse and erode, becoming rubble fields on the sea floor. But while active, they host dense concentrations of life found nowhere else. Vent ecosystems are ephemeral by geological standards. An individual vent might remain active for years or decades, but rarely longer. When it dies, the specialized organisms depending on it must migrate to find new vents or die. Larvae of vent species drift in deep-sea currents, settling where they detect chemical signatures of active vents. This creates isolated populations at different vent sites, separated by miles of barren seafloor. Over evolutionary time, these populations diverge, developing into distinct species found only at specific vent sites. The chemistry of vent fluids and mineral deposits. The chemical composition of hydrothermal vent fluids varies dramatically based on the geological setting, temperature, and the types of rock through which the water circulates. At mid-ocean, ridges, black smoke vents typically discharge fluids with temperatures between 570 and 750 degrees Fahrenheit, though some exceed 800 degrees. These fluids are highly acidic with pH values around 3 to 4, roughly equivalent to vinegar or orange juice. The acidity results from dissolved carbon dioxide and hydrogen sulfide, which form weak acids when combined with water. This acidic water aggressively dissolves metals and sulfur compounds. From the basaltic rock it flows through, creating a chemical soup, rich in iron, copper, zinc, lead, and other elements. The distinctive black colour of black smoke emissions comes from microscopic particles of metal sulfides, particularly iron sulfide, and copper iron sulfide that precipitate instantly when the hot, reduced, metal-rich vent fluid mixes with cold, oxidized seawater. These particles remain suspended temporarily, creating the indesed, smoke-like appearance before settling around the vent. The precipitation occurs because the chemical conditions that kept metals dissolved in the hot vent fluid no longer exist. Once the fluid mixes with seawater, temperature drops, pH changes, and oxygen from seawater causes dissolved metals to combine with sulfide ions, forming solid mineral particles. The mineral deposits building vent chimneys accumulate surprisingly fast. Some black smokers have been documented growing several inches per day when first formed, though growth rates typically slow to inches per month as chimneys mature. The chimney walls contain concentric layers of different minerals, recording changes in fluid composition over time. The innermost layer, in direct contact with the hottest fluid, typically consists of minerals stable at high temperatures like chalcopyrite, a copper iron sulfide. Middle layers contain minerals that precipitate at intermediate temperatures. The outermost layer, exposed to cold seawater, consists of minerals stable at lower temperatures, often including iron sulfides, zinc sulfides, and calcium sulfate. Chemical analysis of these mineral deposits reveals they contain commercially valuable concentrations of copper, zinc, gold, silver. Some extinct hydrothermal vent deposits on land uplifted by tectonic processes millions of years after formation have been mined for these metals. The sulfide deposits at active vents represent potential mineral resources, though extraction would face enormous technical and environmental challenges. Several nations have explored the possibility of deep-sea mining at hydrothermal vents, but concerns about destroying unique ecosystems have prevented commercial operations so far. White smoke vents emit cooler fluids, typically 390 to 570 degrees Fahrenheit, with different chemistry than black smokers. These fluids often have higher pH, sometimes neutral or slightly alkaline, and contain less dissolved metals but more dissolved silica, barium, and calcium. When white smoker fluid meets seawater, minerals like barite, anhydrite, and silica precipitate, building white or pale yellow chimneys. The mineral zonation in white smoker chimneys differs from black smokers, reflecting the different chemistry of the fluids. Some white smokers transition to black smokers or vice versa as the subsurface plumbing system evolves, evident in chimneys showing both white and black mineral layers. Diffuse flow vents represent another type of hydrothermal discharge. These don't build obvious chimneys, but instead release warm water through cracks and porous sediments across broad areas of sea floor. The fluid temperatures range from just above ambient seawater temperature to about 120 degrees Fahrenheit, much cooler than focused black smoker discharge. These diffuse flows result from mixing of hot hydrothermal fluid with cold seawater in the subsurface before emerging at the seafloor. The chemistry of diffuse flows reflects this mixing, showing intermediate compositions between pure vent fluid and seawater. The total heat flux from all hydrothermal vents worldwide amounts to roughly 30% of Earth's total heat loss. This represents an enormous energy transfer from the planet's interior to the oceans. The circulating seawater that feeds hydrothermal systems penetrates several miles into the oceanic crust through cracks and fissures. As it descends, it heats up, reaching temperatures of 570 to 750 degrees Fahrenheit or higher when it encounters hot rock or magma chambers. The heated water becomes less dense and more buoyant, driving it back upward to emerge at vents. This convection system efficiently extracts heat from the oceanic crust. The water circulation through hydrothermal systems profoundly affects ocean chemistry. Estimates suggest the entire volume of Earth's oceans circulates through hydrothermal systems roughly every 10 million years. During this circulation, seawater loses magnesium and sulfate ions, which react with hot rock while gaining metals, silica, calcium, and other elements dissolved from the crust. This process, operating over billions of years, has significantly influenced the chemical composition of seawater. Some scientists argue that without hydrothermal circulation, the oceans would have very different chemistry, possibly less hospitable to life as we know it. Dissolved gases in vent fluids include hydrogen sulfide, methane, carbon dioxide, and hydrogen. The proportions vary based on temperature and rock type. High-temperature vents at mid-ocean ridges produce mostly hydrogen sulfide and carbon dioxide. Lower-temperature vents, particularly those involving serpentinization reactions like the Mariana mud volcanoes, produce large quantities of hydrogen and methane. These reduced gases provide chemical energy that supports chemosynthetic bacteria. The bacteria oxidize hydrogen sulfide or hydrogen or methane using the energy released to fix carbon dioxide into organic molecules. These microbes form the base of vent ecosystems, fulfilling the role that photosynthetic plants and algae play in surface ecosystems. The isotopic composition of vent fluids provides clues about their origin and the reactions they've undergone. Hydrogen isotopes reveal that vent water is mostly seawater that has circulated through the crust, with only minor contributions from magmatic water released from molten rock. Sulfur isotopes indicate that sulfur in hydrogen sulfide comes partly from seawater sulfate, reduced at high temperatures, and partly from sulfur in the rocks themselves. Carbon isotopes show that carbon dioxide in vent fluids has multiple sources, including oxidation of organic matter in sediments, dissolution of carbonate minerals, and release from magma. Rare earth elements in vent fluids show distinctive patterns that differ from seawater. These patterns reflect the minerals that dissolved as fluids circulated through hot rock. By analyzing rare earth element patterns, geochemists can determine the temperature and composition of rocks through which fluids passed, even without directly observing those rocks. This makes rare earth elements powerful tracers of hydrothermal processes. Similarly, the concentrations of dissolved manganese, iron, and other metals that precipitate at different distances from vents can be used to track the dispersal of hydrothermal plumes in the ocean. Some vent fluids contain dissolved organic compounds produced by reactions between water, rock, and carbon dioxide at high temperatures. These abiotic organic synthesis reactions can produce simple organic acids, alcohols, and in some cases more complex molecules like amino acids. The presence of these compounds demonstrates that organic chemistry can occur through purely geological processes without biological involvement. This has important implications for understanding how life might have originated, as early Earth would have had many hydrothermal systems producing organic molecules before life emerged. Some origin of life theories propose that life began at hydrothermal vents, where chemical energy and organic building blocks were abundant. The precipitation of minerals from vent fluids doesn't only build chimneys. Dissolved metals and other elements dispersed in hydrothermal plumes can travel hundreds of miles from their source before precipitating. Iron and manganese precipitate as oxide, particles that settle slowly through the water column, eventually accumulating as ferromanganese deposits on the seafloor, far from any vent. These deposits, called manganese nodules when they form, rounded shapes cover vast areas of the deep ocean floor. They grow extremely slowly, typically less than a millimeter per million years, recording chemical conditions over geological time. Some contain economically significant concentrations of nickel, cobalt, and rare earth elements. making them potential mining targets. Chemosynthetic ecosystems and their bacterial foundation. The discovery of hydrothermal vent ecosystems in 1977 revolutionized biology's understanding of life's possibilities. Before this, scientists assumed all ecosystems ultimately depended on photosynthesis. Plants and algae captured sunlight energy, converting it to chemical energy stored in organic molecules. Herbivores ate the plants. Carnivores ate the herbivores. Every food chain seemed to trace back to photosynthesis. The deep sea appeared to depend on organic matter raining down from the sunlit surface waters. Then scientists aboard the submersible Alvin discovered the first black smoke events at the Galapagos Rift and observed something unprecedented. Dense communities of large animals clustered around the vents, far more life than existed in the surrounding deep sea. The key to these ecosystems is chemosynthesis, a process where bacteria harvest energy from chemical reactions instead of sunlight. The most common form involves oxidizing hydrogen sulfide. Vent fluids contain high concentrations of hydrogen sulfide, toxic to most organisms, but a rich energy source for specialized bacteria. These bacteria, called sulfur oxidizing bacteria or thiotrophs, combine hydrogen sulfide with oxygen from seawater. The reaction releases energy, which the bacteria use to power the synthesis of organic molecules from carbon dioxide. The chemical equation resembles photosynthesis in that carbon dioxide gets reduced to organic carbon, but the energy source is completely different. The bacteria performing chemosynthesis are primary producers, occupying the same ecological role as plants in surface ecosystems. They convert inorganic carbon into organic matter that other organisms can consume. Some bacteria form dense mats on rocks near vents, carpeting surfaces with white, yellow, or orange. Biofilms visible from submersibles. These bacterial mats can reach thicknesses of several inches, representing enormous concentrations of microbial cells. The bacteria reproduce rapidly in the warm, chemical-rich environment, with some species doubling their population every few hours when conditions are optimal. Many larger animals at vents don't eat the bacteria directly, but instead harbour them as symbionts inside their bodies. The giant tubeworm Riftia pachyptala, one of the most iconic vent animals, grows up to 8 feet long and has no mouth, no gut, no way to feed conventionally. Instead, adults possess a specialized organ called a trophosome, packed with sulfur oxidizing bacteria. The tubeworm absorbs hydrogen sulfide and oxygen through its bright red plumes, which contain hemoglobin that binds these molecules. The worm's blood transports hydrogen sulfide and oxygen to the trophosome, where the bacteria use them to produce organic compounds. The bacteria share these nutrients with their host. The tubeworm provides shelter and access to chemicals, the bacteria to provide food. Neither can survive without the other. This symbiosis allows tubeworms to achieve remarkable growth rates, among the fastest known for any invertebrate. Some tubeworms grow several inches per year, reaching maximum size in just a few years. They can live for decades if their vent remains active, possibly over 200 years for some individuals, based on growth ring analysis. Though this remains controversial, when a vent shuts off, tube worms die quickly without the chemical fuel to their bacteria need. Tube worm larvae must find new vents, drifting in deep sea currents until they detect hydrogen sulfide, concentrations indicating an active vent. Vent clams and mussels also harbour bacterial symbionts in their gills. These bivalves extend siphons into vent fluids to absorb hydrogen sulfide, while their gills remain in contact with oxygenated seawater, providing bacteria with both needed chemicals. The bacteria, housed in specialized gill cells, produce organic nutrients that supplement or replace food the clam filters from water. Some vent mussels grow to dinner plate size, far larger than related species living away from vents. Their shells often accumulate sulfide mineral deposits, giving them a dark, tarnished appearance. Not all vent organisms rely on sulfur-oxidizing bacteria. Some bacteria oxidize methane instead, performing methanotrophy. These bacteria combine methane with oxygen, extracting energy to fix carbon dioxide. Methane oxidizing bacteria support their own associated animals, including certain mussels that harbor methanotrophic symbionts rather than sulfur oxidizers. At cold, seeps, where methane bubbles from seafloor sediments without high temperatures, methanotrophic bacteria and their symbiotic partners dominate the ecosystem. The Mariana Trench region includes both hot vents and cold seeps, supporting diverse chemosynthetic communities. Hydrogen oxidizing bacteria represent another group of chemosynthetic microbes, particularly important at serpentinite mud volcanoes. These bacteria oxidize hydrogen gas produced by serpentinization reactions, combining it with oxygen to generate energy. The extremely alkaline conditions at serpentinite vents would kill most organisms, but hydrogen oxidizing bacteria thrive there, forming mats and biofilms that coat surfaces. These bacteria support their own ecosystem of grazers and predators. Adapted to the alkaline environment, scientists have found snails, limpets, and invertebrates invertebrates living on and around serpentinite mud volcanoes, though the communities are less dense than those at black smokers. The bacteria themselves show remarkable diversity. Molecular analysis of vent bacterial communities reveals hundreds of distinct species, many unknown from other environments. Some bacteria live freely in the water. Others form mats. Still others live inside animal tissues. Some tolerate temperatures above 200 degrees Fahrenheit, among the most heat-tolerant organisms known. Others thrive at the cooler margins of vent influence, where temperatures barely exceed ambient deep-sea cold. Some specialize on hydrogen sulfide, others on methane, still others on hydrogen, iron, or manganese. This metabolic diversity allows bacteria exploit virtually every available chemical gradient around vents. Archaea, microorganisms distinct from bacteria, though similar in size and appearance, also inhabit vents in large numbers. Some archaea are hyperthermophiles, organisms that grow best at temperatures above 175 degrees Fahrenheit. The current record holder for high temperature growth is Methanoperus candleri, an archaeon that can reproduce at 252 degrees Fahrenheit, approaching water's boiling point at sea level, though not at depth, where pressure raises the boiling point. These hyperthermophiles possess specialized proteins and membranes that remain stable at temperatures that would cook normal organisms. Their cell membranes contain unusual lipids that don't fall apart at high temperatures. Their DNA-binding proteins protect genetic material from heat damage. Some scientists hypothesize that the earliest life on Earth resembled these hyperthermophilic archaea, evolving in hot environments similar to modern hydrothermal vents. This remains debated, with others arguing that early life was only moderately thermophilic or even mesophilic, preferring moderate temperatures. However, the tree of life's deepest branches include many thermophiles, suggesting heat tolerance is an ancient trait. Whether life originated at vents or not, the chemosynthetic organisms there demonstrate that life doesn't require sunlight. Only chemical disequilibrium, any situation where chemicals want to react but can't without biological catalysis. The total biomass at hydrothermal vent ecosystems far exceeds that of surrounding deep-sea areas. While typical deep-sea sediments might support a few grams of living organisms per square meter, vent areas can have several kilograms per square meter, thousands of times denser. This biomass exists despite the ephemeral nature of individual vents. The high productivity stems from the abundant chemical energy supplied continuously by hydrothermal circulation. As long as hot fluid flows, energy flows, supporting dense populations. When flow stops, the ecosystem collapses within months as animals die or migrate. Giant tube worms and extreme survival mechanisms. Riftia pachyptela, the giant tube worm, exemplifies biological adaptation to extreme environments. These animals have no mouth, no anus, no stomach, no intestines, none of the digestive apparatus typical of animals. Adult tube worms consist primarily of a white, chitinous tube that protects the soft body within, a bright red plume that extends from the tube opening, and internally the trophosome tissue packed with bacteria. The plume contains hemoglobin at concentrations higher than human blood, giving it a vivid crimson colour. This hemoglobin simultaneously binds oxygen, carbon dioxide, and hydrogen sulfide, a remarkable feat since hydrogen sulfide normally poisons hemoglobin by binding irreversibly to it. Tubeworm hemoglobin has a special structure that prevents hydrogen sulfide from permanently blocking oxygen binding sites. The molecule contains multiple binding sites positioned so that hydrogen sulfide and oxygen don't interfere with each other. Additional proteins in tubeworm blood protect cells from hydrogen sulfide toxicity. Hydrogen sulfide, toxic because it blocks cellular respiration by inhibiting cytochrome C oxidase in mitochondria, gets kept away from the tubeworm's own cells until delivered to bacteria. The bacteria, resistant to hydrogen sulfide, since they use it as an energy source, process the chemical safely. The trophosome occupies most of the tubeworm's internal volume. This tissue contains bacteriocytes, specialized cells that house the bacterial symbionts. Each bacteriocyte contains thousands of bacteria surrounded by the host cell's membrane. The bacteria remain isolated from the tube worm's circulatory system, receiving nutrients and chemicals through controlled transfer across membranes. The tube worm supplies the bacteria with hydrogen, sulfide, oxygen, and carbon dioxide. The bacteria produce organic compounds including sugars, amino acids, and other nutrients. These leak or are transported out of the bacteria, absorbed by the host cell and distributed through the tube worm's body. Tube worms acquire their bacteria from the environment rather than inheriting them from parents. Tube worm larvae hatch without symbionts, swimming briefly as free-living organisms before settling near a vent. Upon settling, the larvae have a functional gut, which they use to ingest sulfur-oxidizing bacteria from the surrounding water. The bacteria colonize the larva's gut, which then undergoes remarkable transformation. The gut closes off and transforms into the trophosome. The mouth and anus seal shut permanently. The digestive system disappears, replaced by the symbiotic organ. This developmental transformation represents one of the most extreme modifications known in animal development. Adult tube worms can regulate their exposure to vent fluid by extending or retracting their plumes and by moving slightly within their tubes. When hydrogen sulfide concentrations get too high or oxygen too low, tube worms retract their plumes into their tubes and seal the opening. This protects them from dangerous conditions, but also cuts off their food supply since bacteria need continuous access to chemicals. Tube worms must balance chemical acquisition against toxicity, risk extending plumes when conditions permit, retracting them when necessary. The growth rate of tube worms depends on the chemical flux at their location. Tube worms living in areas with high hydrogen sulfide and oxygen concentrations grow faster than those in less favorable positions. This creates intense competition for prime real estate. Near active vents, tube worm aggregations can reach densities of 350 individuals per square meter, creating forests of white tubes with waving red plumes. These aggregations modify local conditions, their plumes affecting water flow and chemical distribution. The tubes persist after tube worms die, creating structure that other organisms colonize. Tube worms face multiple threats beyond vent shutdown. Vent crabs prey on tube worms, climbing the tubes to bite off plumes. The tube worm can regenerate a lost plume, though this requires energy and time. Fish visit vents to feed on tube worms and other vent fauna, though they cannot live there permanently due to the toxic chemicals. Some fish have adapted high tolerance to hydrogen sulfide, allowing them to venture close to vents briefly to feed. Predation creates a selective pressure favoring faster growth and larger size, since bigger tube worms are harder for predators to kill. Temperature tolerance in tube worms is limited despite their association with hot vents. The tube worm body must remain below about 140 degrees Fahrenheit to survive. They achieve this by positioning themselves where mixing of hot vent fluid and cold. Seawater creates tolerable temperatures, typically in the range of 35 to 90 degrees Fahrenheit. The bacteria they harbour also have temperature limits, unable to function above certain thresholds. This restricts tube worms to areas where fluid is sufficiently diluted by seawater mixing, typically inches to feet away from the known hottest discharge points. Pressure apparently doesn't limit tube worms. They've been found at vents ranging from 8,200 feet to over 13,000 feet depth, spanning pressure ranges from 250 to 400 atmospheres. Their soft bodies contain no gas spaces that would compress under pressure, and their biochemistry functions normally across this pressure range. Pressure-adapted proteins maintain proper function regardless of depth. This contrasts with many surface organisms whose proteins denature or malfunction at high pressure. Tubeworm reproduction involves broadcasting gametes into the water. Males release sperm while females release eggs, fertilization occurring externally. The larvae that result are planktonic, drifting in deep-sea currents. Most larvae die never finding a suitable vent to settle on. The ocean's vastness and vents' rarity make successful settlement extremely unlikely for any individual larva. However, tubeworms produce enormous numbers of larvae, and ocean currents connect different vent sites, allowing dispersal across distances of dozens or even hundreds of miles. Genetic analysis of tubeworm populations at different vents reveals they're not completely isolated, indicating larvae successfully traverse the deep sea to colonize new sites. The evolutionary origin of tubeworms remains unclear. They belong to the annelid worms, the same group that includes earthworms and marine polychaetes. Molecular phylogenies indicate that vent tubeworms are closely related to certain shallow water tube-dwelling worms. The ancestor of Riftia probably lived in shallow sediments, possessing a normal gut and feeding on organic matter. At some point, this ancestor colonized deep-sea reducing environments, perhaps first at cold seeps or organic falls where hydrogen sulfide is present, symbiosis with sulfur oxidizing. Bacteria evolved, providing advantage in these chemical-rich but food-poor environments. The gut became reduced as symbiosis became obligate. Eventually, descendants colonized hot vents where chemical energy was even more abundant. This evolutionary trajectory from normal feeding to symbiotic dependence occurred multiple times independently in different animal groups, suggesting symbiosis is a common solution to deep-sea life. Vent shrimp and specialized sensory adaptations. Among the strangest creatures at hydrothermal vents are the vent shrimp, particularly species of Rimicaris found at mid-Atlantic ridge vents. These shrimp swarm around black smokers in densities reaching 3,000 individuals per square meter, creating living carpets of crustaceans. Their bodies are pale, almost translucent, with one immediately obvious peculiarity: they lack normal eyes. Where eyes should be, they have large patches of reflective tissue on their backs. These structures, initially puzzling to scientists, turn out to be modified eyes adapted for a unique purpose, detecting the faint thermal radiation emitted by hot vent water. Normal eyes detect visible light photons with wavelengths around 400 to 700 nanometers, but no visible light exists at vent depths, except bioluminescence. However, hot objects emit infrared radiation, thermal radiation with longer wavelengths than visible. light. A black smoker at 750 degrees Fahrenheit emits measurable infrared radiation, extremely faint but detectable with sufficiently sensitive equipment. The vent shrimp's dorsal eye patches contain rhodopsin, the light-sensitive protein found in normal eyes, but modified to respond to the near-infrared wavelengths emitted by hot vents. This allows the shrimp to see heat navigating toward warm water where bacterial food grows. The shrimp position themselves in the boundary zone where hot vent fluid mixes with cold sea water, where temperatures range from 50 to 105 degrees Fahrenheit. Too close to the vent and they would cook. Too far away and bacterial productivity drops too low. The thermal eyes let them maintain optimal position despite the complete darkness. This represents a unique sensory adaptation found nowhere else in the animal kingdom. While some snakes can detect infrared radiation using specialized pit organs, no other animal uses modified eyes for this purpose. Vent shrimp feed by scraping bacterial mats from rock surfaces with their mouthparts. Some species also harbor bacterial symbionts in their gill chambers, similar to vent mussels. These bacteria supplement the shrimp's diet, providing additional nutrients. The combination of grazing and farming bacteria allows vent shrimp to exploit multiple food sources, making them highly successful at vents where they occur. Not all vent sites have. Shrimp, though, Pacific vents tend to be dominated by tube worms, clams, and mussels, while mid-Atlantic ridge vents often support dense shrimp populations. The reasons for this biogeographic difference aren't fully understood, but may relate to differences in vent chemistry, temperature, or historical factors governing which species first colonized different regions. Other crustaceans at vents show different adaptations. Vent crabs, genus Bythogria, are active predators with functional eyes. Though these are adapted to low light conditions, the crabs scavenge dead animals and actively hunt live prey, including tube worms, mussels, and smaller invertebrates. They can tolerate higher temperatures than most vent animals, venturing close to vent openings to feed. Their walking legs are long and adapted for moving across the complex topography of lava flows and mineral deposits. Unlike the shrimp, crabs don't rely on chemosynthetic bacteria for food, but instead feed on animals that do, making them secondary consumers in the vent ecosystem. Barnacles at vents present another interesting case. These crustaceans cement themselves to rocks near vents, filtering bacteria and organic particles from the water. Some vent barnacles reach remarkably large sizes, their shells several inches across. They extend feathery appendages called cirri to sweep through the water, collecting food particles the barnacles must cope with fluctuating temperatures and chemical concentrations as vent output varies. They can retract their cirri and close their shell plates when conditions become unfavorable, waiting out periods of excessive heat or hydrogen sulfide concentration. Amphipods, small shrimp-like crustaceans, swarm at some vent sites in enormous numbers. These scavengers feed on dead organisms and organic debris. When scientists deploy bait dead fish or other organic material, amphipods arrive within minutes, covering the bait completely. Their ability to detect chemical signals from decaying organic matter over considerable distances demonstrates highly sensitive chemoreceptors. Some amphipod species show extreme tolerance to hydrogen sulfide and low oxygen, allowing them to exploit food sources in areas where other scavengers cannot survive. The sensory challenges at vents extend beyond vision. Chemical sensing becomes critical for navigation, food finding, predator avoidance. Many vent animals have enlarged antennae, other chemosensory structures. They detect gradients of hydrogen, sulfide, methane, and other vent chemicals, using these to orient themselves relative to vents. Some species can distinguish between different types of bacterial mats by their chemical signatures, allowing them to select preferred food sources. Temperature sensing must be extremely precise for animals living. In vent environments, temperature can change by tens of degrees, over distances of inches. Animals need to detect these gradients to maintain safe positions. Some vent organisms have thermoreceptors sensitive to temperature differences of less than 1 degree Fahrenheit, allowing fine-scale positioning in the thermal landscape. This sensitivity rivals or exceeds that of temperature-sensing neurons in mammals. Mechanoreception, sensing water movement and vibration, helps vent. Animals detect predators and navigate currents. The turbulent flow around vents creates complex patterns that animals can sense and use for orientation. Some species position themselves in specific flow regimes, using water movement to deliver food particles or chemical signals. Specialized hair-like structures on legs, antennae, and bodies detect water motion at scales relevant to their size. The absence of day-night cycles in the deep sea eliminates the environmental cues most organisms use to regulate daily rhythms. Yet some vent animals show behavioral rhythms anyway, suggesting internal biological clocks independent of light. The function of these rhythms in constant darkness isn't clear, but they may help coordinate reproductive activities or optimize feeding behavior in ways that don't require light cues. Vent octopuses and deep-sea reproduction strategies. In 2005, researchers using a remotely operated vehicle discovered unusual octopuses at hydrothermal vents along the Juan de Fuca ridge off Washington state. These pale, ghostly octopuses clustered near warm water seeping from cracks in the lava, their bodies positioned directly on rocks in areas where temperature reached 60 to 70 degrees Fahrenheit. Most deep-sea octopuses avoid such warm areas, preferring the stable cold of the deep ocean. The vent octopuses, belonging to a previously unknown genus later, named Granaldoni, exhibited bizarre behavior. They weren't feeding, they weren't moving much, they were brooding eggs. Female octopuses lay eggs and guard them until hatching, a period that varies by species from weeks to months. The vent octopuses were guarding egg clutches, but the eggs seemed unusually well developed, suggesting they'd been there a long time. The researchers marked individual females with paint spots and returned months later. The same females were still there, still guarding the same egg clutches. Over 4 years of monitoring, one particular female, dubbed Octomom by the research team, remained on the same rock outcrop, never leaving, never feeding, continuously brooding her eggs. The brooding period lasted 53 months, 4.5 years, longest known for any animal species. During this time, the female octopus didn't eat. She slowly wasted away, her body consuming itself to stay alive long enough for her eggs to develop. Octopuses die after reproducing, their death programmed by hormonal changes that occur once eggs are laid. But most species die weeks or months after laying eggs. This vent octopus prolonged the dying process to an extreme, surviving without food for over 4 years through sheer metabolic slowdown. Why such an extraordinarily long brooding period? Temperature provides the answer. The warm water near the vent, while warmer than the surrounding deep sea, remains relatively cool at 60 to 70 degrees Fahrenheit. Embryonic development proceeds faster at warmer temperatures but slower in cold. The vent octopus eggs developed at near minimum temperature for development to proceed at all. Had the female laid eggs in the typical deep sea temperature of 35 degrees Fahrenheit, embryos might not develop at all or would take even longer. By positioning herself at a vent where water was marginally warmer, she accelerated development compared to cold water but still faced years of waiting. The eggs couldn't survive at higher temperatures. Octopus embryos are sensitive to heat, developing abnormally or dying if exposed to excessive warmth. The mother positioned her eggs at the maximum temperature they could tolerate, the warmest location that wouldn't kill them, but as warm as possible to minimize development time. This represents an exquisite balance between conflicting requirements. The female's choice of brooding site determined whether her offspring would survive, making site selection perhaps the most important decision of her reproductive life. During the brooding period, the female octopus actively maintained her eggs, cleaning them with her arms to prevent bacterial, fungal growth. Dead or infected eggs would contaminate healthy ones, so constant vigilance was necessary. The female used her siphon to direct water flow over the eggs, ensuring adequate oxygen supply. Octopus eggs respire, consuming oxygen and producing carbon dioxide. Without water circulation, eggs in the center of the clutch would suffocate. The mother's continuous fanning motion maintained life-sustaining conditions for all her eggs. Other deep-sea organisms show similarly extreme reproductive strategies. Some deep-sea fish produce only dozens of eggs rather than the millions typical of shallow water species. Each egg is large, packed with yolk to sustain the embryo through extended development. The larvae hatch at an advanced stage of development, better equipped to survive in the food-poor deep sea than tiny, helpless larvae would be. This represents a classic quality versus quantity trade-off. Fewer offspring, but each with higher survival probability, can be advantageous when environmental conditions make survival difficult. Deep-sea anglerfish exhibit perhaps the most bizarre reproductive adaptation. Females grow to substantial size, up to 3 feet, long in some species, while males remain tiny, sometimes less than an inch long. When a male encounters a female, he bites into her body and fuses with her permanently. His tissues merge with hers, his circulatory system connects to hers, and he becomes essentially a parasitic appendage providing sperm when needed. Male loses all independence, receiving nutrients from the female's bloodstream while providing reproductive services. Some female anglerfish carry multiple males fused to their bodies simultaneously. This extreme sexual dimorphism and parasitic mating evolved because finding mates in the vast, dark, deep sea is extraordinarily difficult. A male anglerfish might encounter only one female in his entire life. Rather than risk losing this opportunity, he commits completely, sacrificing independent existence for guaranteed reproductive success. The female benefits by having sperm available whenever she's ready to spawn, without needing to find males repeatedly. Both sexes maximize reproductive success through this bizarre arrangement. The fusion process involves sophisticated immunological mechanisms. Normally, grafting tissue from one individual to another triggers immune rejection. The recipient's immune system recognizes foreign tissue and attacks it, yet male anglerfish successfully fuse with females, their tissues accepted rather than rejected. Research has revealed that these species have highly reduced immune systems, lacking many components of the adaptive immune system that other vertebrates possess. This immunological suppression allows tissue fusion, but potentially leaves anglerfish more vulnerable to parasites and diseases. Many deep-sea invertebrates use broadcast spawning, releasing eggs and sperm into the water where fertilization occurs externally. This seems risky in the sparse deep sea, where individuals of the same species may be widely scattered. However, chemical signals can coordinate spawning. When one individual releases gametes, chemical cues trigger nearby individuals to spawn simultaneously, increasing fertilization probability. Some species spawn in response to specific environmental triggers such as temperature changes or current patterns, synchronizing reproduction across populations. The larvae of many deep-sea vent species are planktonic, drifting in ocean currents for weeks or months. These larvae must feed during their planktonic phase, but food is scarce in the deep sea. Some larvae have been observed rising hundreds or even thousands of feet above the seafloor, ascending toward more productive surface waters where food is more abundant. After feeding and growing in the shallower water, they descend again to find suitable settlement sites near vents. This vertical migration exposes larvae to very different environmental conditions, including lower pressure, higher temperature, and predators they wouldn't encounter in the deep sea. The timing of larval release can be critical. Some species release larvae when currents are favourable for transport to other vent sites. Others release larvae continuously, betting that at least some will encounter suitable conditions. The balance between these strategies depends on how predictable environmental conditions are and how far larvae need to travel to find new habitat. Other species produce leucothotrophic larvae that don't feed, instead relying entirely on yolk reserves provided by the mother. These larvae can survive longer without food, but are limited by how much yolk the mother can pack into each egg. The trade-off between producing many small eggs with feeding larvae versus fewer large eggs with non-feeding larvae depends on the specific environmental conditions, and predation pressures each species faces. Pressure adaptation in trench dwelling. Organisms. At the bottom of the Mariana Trench, pressure exceeds 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This creates fundamental challenges for biological molecules and cellular structures. Proteins fold into specific three-dimensional shapes that determine their function. Pressure affects protein folding, potentially causing proteins to misfold or aggregate. Cell membranes must maintain proper fluidity to function. Too rigid and transport across membranes fails, too fluid, and membranes lose structural integrity. Pressure affects membrane fluidity, making membranes more rigid at high pressure. Organisms living at extreme depths require specialized molecular adaptations to maintain normal cellular function. The deepest living fish ever recorded was captured at 27,460 feet in the Mariana Trench during a 2014 expedition. The fish, a snailfish of the genus Pseudoliparis, appeared remarkably delicate, with translucent skin, small eyes, and a tadpole-like body. It seemed fragile, yet it thrived at pressures that would crush most organisms. When researchers examined related snailfish species from various depths, they discovered that deeper living species had specific genetic adaptations absent in shallow water relatives. One key adaptation involves the protein trimethylamine N oxide, abbreviated TMAO. This small organic molecule accumulates in the tissues of deep-sea fish at concentrations directly correlated with depth. Shallow water fish have low TMAO concentrations, while hadal zone fish have extremely high concentrations. TMAO acts as a piezolyte, a pressure-protecting solute that counteracts pressure's effects on proteins and membranes. The molecule stabilizes protein structure under pressure, preventing the distortions that would otherwise disrupt function. It also maintains membrane fluidity by inserting between lipid molecules, preventing excessive rigidity. The TMAO concentration in hadal fish reaches levels that would be toxic to surface organisms. At Challenger Deep, fish tissues contain TMAO concentrations approaching 400 millimoles per litre, roughly 20 times higher than in shallow water species. This represents a remarkable biochemical adaptation. The cellular machinery adjusted to function with TMAO concentrations that would poison cells adapted to surface conditions. The evolutionary acquisition of high TMAO tolerance enabled colonization of the deepest ocean zones. However, TMAO accumulation creates its own limit to depth range. Above certain concentrations, TMAO begins interfering with cellular processes rather than protecting them. Calculations based on TMAO concentrations in known fish suggest that fish cannot to survive below approximately 27,900 feet, remarkably close to the maximum depth where fish have actually been observed. Below this depth, the TMAO concentration required to counteract pressure would exceed the concentration cells can tolerate. This creates a hard biochemical limit to how deep fish can live. Other organisms use different strategies. Amphipods, shrimp-like, crustaceans, have been captured from the deepest parts of Challenger Deep at 36,000 feet. These animals obviously don't rely solely on TMAO for pressure adaptation, since they live far deeper than the calculated fish limit. Research on hadal amphipods reveals modifications to membrane lipid composition, deep sea. Amphipods have membranes enriched in polyunsaturated fatty acids, which remain fluid at high pressure and low temperature. The specific types of polyunsaturated fatty acids present in hadal amphipods differ from those in shallow water species, representing evolutionary fine-tuning of membrane composition. Pressure also affects enzyme function. Enzymes are proteins that catalyze biochemical reactions, and their activity depends on maintaining proper three-dimensional structure. Pressure can compress the spaces within enzyme molecules, changing their shape and reducing catalytic efficiency. Deep-sea organisms produce enzyme variants with altered amino acid sequences that maintain function under pressure. These pressure-adapted enzymes may function poorly at surface pressure, representing a trade-off. Adaptation to one pressure regime can reduce fitness at other pressures. The lactate dehydrogenase enzyme, crucial for cellular energy metabolism, shows clear depth-related adaptations. This enzyme has been studied in fish from various depths. Shallow water fish have lactate dehydrogenase variants that work efficiently at atmospheric pressure but lose activity at high pressure. Deep sea fish have variants that maintain activity at high pressure but function less efficiently at atmospheric pressure. The amino acid differences between shallow and deep variants cluster in regions of the protein where pressure effects are most pronounced, strong evidence that natural selection has optimized these enzymes for their specific pressure environments. Muscle protein myosin also shows pressure adaptations. Myosin generates the force for muscle contraction, a process involving large conformational changes in the protein structure. Pressure resists these conformational changes, potentially impairing muscle function. Hadal fish and invertebrates have myosin variants that maintain contractile function at extreme pressure. The specific adaptations vary between species, indicating that multiple evolutionary solutions exist to the pressure problem. DNA stability is affected by pressure, though less dramatically than proteins. The hydrogen bonds holding DNA's double helix together can be disrupted by extreme pressure. However, cells contain numerous proteins that bind to and stabilize DNA, and these DNA-binding proteins show pressure adaptations in deep-sea species. Histones, proteins around which DNA wraps in the cell nucleus, have modified amino acid sequences in some hadal organisms. These changes enhance DNA histone binding at high pressure, maintaining proper DNA organization despite challenging conditions. Cell division machinery faces pressure challenges. Mitosis and meiosis involve extensive reorganization of cellular components, with chromosomes condensing, the nuclear envelope breaking down, and spindle fibers pulling chromosomes apart. These processes require precise spatial and temporal coordination of numerous proteins. Pressure could disrupt this coordination, causing cell division errors. Deep-sea organisms have cell division machinery, adapted to function reliably at high pressure, though the specific molecular adaptations remain incompletely understood. Neurotransmission also requires pressure-resistant mechanisms. Nerve cells communicate by releasing neurotransmitter molecules that bind to receptors on other cells. This process involves fusion of membrane vesicles with the cell membrane, release of neurotransmitter into the synaptic cleft, binding to receptors, and subsequent signal transduction. Each step involves protein conformational changes, potentially sensitive to pressure. Deep sea fish maintain normal neural function at extreme depths, indicating their neurotransmission machinery is pressure adapted. Some microorganisms, isolated from hadal trenches, are pisophiles, organisms that grow best at high pressure. These bacteria and archaea not only tolerate extreme pressure, but actually require it for optimal growth. Brought to surface pressure, they grow slowly, or not at all. Pisophiles represent the opposite extreme from surface organisms adapted so completely to high pressure that low pressure becomes the stressor. These microbes have fundamentally different cellular organization compared to surface relatives, with every aspect of their biology optimized for life under pressure. The Mariana snailfish and Hadal zone. Predators. The Mariana snailfish, Pseudoliparis swirei, holds the record as the deepest living fish ever caught and filmed. Described scientifically in 2017, this species lives at depths between 22,000 and 26,200 feet in the Mariana Trench. The fish appears almost ghostly. Its body is translucent with pinkish white coloration, allowing internal organs to be visible through the skin. It grows to about 11 inches in length and has a tadpole-like shape with a large head, small eyes, and a tapering body ending in a delicate tail. Unlike many deep-sea fish with fearsome teeth and bioluminescent lures, the Mariana snailfish looks surprisingly innocuous. The translucent skin results from an almost complete lack of pigmentation and scales. Surface fish need pigments for protection against ultraviolet radiation and for camouflage. In the hadal zone's absolute darkness, these functions are unnecessary. The elimination of pigment production saves metabolic energy, a valuable economy in the food-limited deep sea. The scaleless skin reduces weight and swimming drag, improving energy efficiency. Every feature of the Mariana snailfish reflects optimization for life in extreme conditions where energy conservation is critical. The small eyes might seem surprising. Some deep-sea fish have enormous eyes to capture minimal light from bioluminescence. Others have reduced or absent eyes, having lost vision entirely in the lightless abyss. The Mariana snailfish retains functional eyes, though smaller than shallow water relatives. Research suggests these eyes detect bioluminescence from prey items, primarily small crustaceans that produce light. The eyes are positioned to look upward, where any available light would most likely appear. This upward gaze allows the snailfish to detect the silhouettes of prey against any background light, however faint. The skull structure shows remarkable adaptations to pressure. Unlike most fish skulls, which are extensively ossified with numerous bones fused together, The Mariana snailfish has a poorly ossified skull with many gaps and flexible joints. This reduces the skull's mechanical strength, but also eliminates enclosed spaces where pressure differentials could develop. The brain sits in a partially open cranium, directly exposed to surrounding tissues. While this seems to leave the brain vulnerable, it actually protects it from pressure damage by eliminating trapped spaces that could compress under pressure. The fish lacks a swim bladder, the gas-filled organ that provides buoyancy in many shallow water fish. Swim bladders cannot function at hadal depths where pressure would compress any gas to essentially zero volume. Instead, the Mariana snailfish achieves near neutral buoyancy through high water content in its tissues and a large fatty liver. The liver comprises a substantial portion of body mass and contains oils less dense than water, providing lift. This solution avoids the impossible physics of gas bladders while maintaining buoyancy necessary for efficient swimming. The lateral line system, sensory organs that detect water movement and allow fish to sense nearby objects and water currents, is well developed in the Mariana snailfish. In the dark hadal zone, mechanosensation becomes more important than vision for detecting prey and avoiding obstacles. The lateral line consists of fluid-filled canals with sensory hair cells that bend in response to water movement. These organs function effectively at high pressure, providing the fish with awareness of its immediate environment despite the darkness. Stomach contents of captured specimens reveal the diet consists primarily of small crustaceans, particularly amphipods. The Mariana snailfish is a predator, actively hunting mobile prey. Rather than scavenging or filter feeding, its teeth are small but sharp, suitable for grasping soft-bodied invertebrates. The jaw? Mechanics allow rapid strikes to capture amphipods before they escape. Prey abundance at hadal depths is limited, so the snailfish cannot afford to be a specialized feeder. It consumes whatever amphipods and other small invertebrates it encounters. Reproductive biology remains largely unknown due to difficulty in observing these fish alive. No larvae or juveniles have been captured, leaving their early life history mysterious. Adult females captured contained well-developed eggs, indicating they produce relatively small numbers of large eggs like other deep-sea fish. The large egg size suggests each offspring receives substantial yolk reserves to survive the food-poor environment. Where spawning occurs and how long development takes remain unanswered questions. Population density appears extremely low based on video observations. During extended ROV dives covering large areas of seafloor, only occasional snailfish are observed, never large aggregations. This low density makes finding mates challenging. Chemical communication likely plays a role, with fish detecting pheromones released by potential mates from considerable distances. The ability to locate mates despite sparse populations is essential for reproductive success. The Mariana snailfish faces predation pressure from larger hadal invertebrates. Large amphipods, some exceeding 12 inches in length, are aggressive predators that attack dead or weakened fish. Whether they prey on healthy snailfish is unknown, but they certainly scavenge any dead ones. Other potential predators include unidentified hadal organisms that may hunt fish. The ecosystem's trophic structure remains incompletely understood, with many predator-prey relationships still being discovered. Competition for food among hadal predators must be intense given the limited prey availability. The snailfish's ability to actively swim and hunt gives it advantages over slower-moving invertebrate predators. However, invertebrates can access smaller spaces in rocky terrain where fish cannot follow. This spatial partitioning reduces direct competition, allowing multiple predator species to coexist. The lifespan of Mariana snailfish is unknown but likely considerable. Deep-sea fish generally have slow metabolisms, grow slowly, and live longer than shallow water relatives. Some deep-sea fish live 100 years or more. The Mariana snailfish may have similarly extended lifespans, though proving this would require marking individuals and monitoring them over decades, technically difficult at hadal depths. Genetic analysis reveals the Mariana snailfish is closely related to other hadal snailfish species found in different trenches. Each trench has its own species, with limited genetic exchange between trenches. The trenches are isolated from each other by thousands of miles of shallower seafloor, creating barriers to dispersal. This isolation has driven speciation, with each trench hosting unique fish species that evolved independently after their ancestors colonized that particular trench. The pattern mirrors island biogeography, where isolated habitats develop distinct species assemblages, amphipod scavengers, and the hadal food web. Amphipods dominate the hadal zone's scavenger guild, arriving rapidly at any food fall to the trench floor. These crustaceans, distant relatives of shrimp, range from thumbnail-sized individuals to giants exceeding 12 inches in length. The largest amphipods in the world live in the hadal zone, several times bigger than their shallow water relatives. This phenomenon, called abyssal gigantism when occurring in deep water, and hadal gigantism, specifically in trenches, results from multiple factors including cold temperatures, high oxygen availability, and food scarcity that favours larger body size. Hirondelia gigas, one of the largest hadal amphipods, reaches lengths of 13 inches. The species has been captured from multiple trenches including the Mariana, Kermadec, and Japan trenches, living at depths exceeding 32,000 feet. These giants appear alien, with long antennae, stalked eyes, and powerful clawed legs adapted for gripping food and substrates. Their bodies are pale, nearly colourless, with translucent exoskeletons that reveal internal structures. The cuticle contains high concentrations of aluminum, unusual for biological tissues. The aluminium apparently strengthens the exoskeleton, providing structural support without excessive weight. Amphipods are scavengers, feeding on organic matter that falls to the trench floor. In the hadal zone, virtually all food arrives from above: dead fish, whales, squid, zooplankton, and other organisms that die in shallower waters and sink. This falling organic matter, called nekton, falls when it's large, like a whale carcass, or marine snow when its small particles, represents the primary energy input to hadal ecosystems. Without this rain of food from above, the trenches would be biological deserts. Scientists study Hadal scavenging by deploying baited traps. A trap consists of a metal frame with bait inside, usually mackerel or sardines, obtained from local markets attached to floats and anchor weights. The trap is dropped overboard and falls to the trench floor. After a set time, usually 12 to 24 hours, acoustic signal triggers release of the anchor weight and the trap rises to the surface carried by the floats. Cameras attached to the trap frame record activity, showing what organisms arrive to feed. The footage reveals amphipods arrive within minutes once bait odour spreads through the water. Chemoreceptors on their antennae detect food molecules at extremely low concentrations, allowing them to track odour plumes to the source. The first arrivals attract more amphipods, possibly because active feeding releases additional chemical signals. Within hours, hundreds or thousands of amphipods can swarm a small bait item. Their combined feeding stripping flesh from bones in remarkably short time. A dead fish weighing several pounds can be reduced to a skeleton in less than 24 hours. This rapid scavenging makes sense given the rarity of food falls. Amphipods cannot afford to feed slowly when competition is intense. The first individuals to detect a food fall consume the most. Later rivals get scraps or nothing. Natural selection strongly favours rapid detection and quick feeding, resulting in the efficient scavenging behaviour observed. Microbial life and the limits of biology. The sediments at the bottom of the Mariana Trench harbour the most extreme microbial communities on Earth. Core samples extracted from Challenger deep reveal bacteria and archaea living in conditions that push the boundaries of what biology can tolerate. These microorganisms exist under pressures exceeding 16,000 pounds per square inch, temperatures just above freezing, complete darkness, and with minimal nutrients. Yet, they not only to survive, they actively metabolize, reproduce, and maintain complex biochemical processes that would fail in surface organisms exposed to similar pressure. The bacterial cell envelope, the outer membrane and cell wall that contains cellular contents, must withstand enormous compressive forces without collapsing or rupturing. Surface bacteria brought to trench pressures die instantly as their membranes fail. Piezophilic bacteria, those adapted to high pressure, possess modified membrane lipids with higher proportions of unsaturated fatty acids. These lipids remain fluid at pressure and low temperature, maintaining membrane function. The specific fatty acid composition varies between species, with the deepest dwelling microbes showing the highest degree of unsaturation, some HADL. Bacteria synthesize unique fatty acids found nowhere else, molecular innovations that evolved specifically for extreme pressure tolerance. The cytoplasm inside bacterial cells contains thousands of proteins, each folded into precise three-dimensional structures necessary for function. Pressure distorts protein structures by compressing internal cavities and forcing amino acid side chains closer together. This compression disrupts the delicate balance of forces, hydrogen bonds, electrostatic interactions, hydrophobic effects that maintain proper protein shape. Piezophilic bacteria produce pressure-adapted proteins with amino acid sequences, optimized to maintain function under compression. These modifications often involve replacing bulky amino acids with smaller ones in pressure-sensitive regions, eliminating internal cavities where compression would be most severe, and strengthening, stabilizing interactions, DNA replication and transcription, fundamental processes for all. Life require numerous proteins to function in coordinated fashion. DNA polymerase must unwind the double helix, separate the strands, and synthesize new complementary strands. RNA polymerase must transcribe DNA sequences into messenger RNA. Both processes involve large conformational changes in protein structures as they move along DNA. Pressure impedes these conformational changes, potentially slowing or stopping DNA replication and transcription. Haydal bacteria have evolved modified versions of these essential enzymes that maintain activity at extreme pressure, ensuring genetic information can be copied and expressed even in the trench's crushing conditions. Ribosomes, the molecular machines that synthesize proteins, consist of ribosomal RNA and dozens of ribosomal proteins assembled into complex structures. The ribosome must maintain precise geometry to position, transfer RNAs correctly, and catalyze peptide bond formation between amino acids. Pressure could compress the ribosome, misaligning its components and disrupting protein synthesis. Studies of ribosomes from piezophilic bacteria reveal structural modifications that resist compression. The ribosomal RNA contains additional stabilizing base pairs, and ribosomal proteins have altered sequences that strengthen ribosome assembly. These changes preserve translation accuracy at pressures that would disrupt ribosomes from surface organisms. Energy metabolism in Haydal bacteria exploits various chemical gradients. Some species oxidize organic matter that settles from above using electron acceptors like oxygen, nitrate, or sulfate, dissolved in seawater. Others perform fermentation, breaking down organic molecules without external electron acceptors. Still, others derive energy from inorganic chemical reactions, oxidizing hydrogen, methane, ammonia, or reduced iron and manganese. This metabolic diversity allows bacterial communities to extract energy from every available chemical source, maximizing efficiency in the nutrient-poor environment. Methane cycling in trench sediments involves multiple bacterial groups working in sequence. Organic matter buried in sediments undergoes anaerobic decomposition by fermentative bacteria, producing simple organic acids, hydrogen, and carbon dioxide. Methanogenic archaea consume these products, generating methane as a metabolic waste product. The methane diffuses upward through sediment layers until reaching zones where oxygen or sulfate are present. There, methanotrophic bacteria oxidize the methane, converting it back to carbon dioxide and biomass. This cycling processes carbon through multiple forms, with different microbial groups specialized for each transformation. Nitrogen cycling follows similar complexity. Organic nitrogen in dead organisms gets decomposed to ammonia by heterotrophic bacteria. Ammonia oxidizing bacteria and archaea convert ammonia to nitrite, deriving energy from this oxidation. Nitrite oxidizing bacteria further oxidize nitrite to nitrate. Other bacteria reduce nitrate back to nitrogen gas through denitrification, completing the cycle. Each step requires specialized enzymes and is performed by distinct microbial groups. The Hadal nitrogen cycle operates at far slower rates than in surface sediments due to low temperature, high pressure, and limited nutrient availability, but the same fundamental biochemical pathways function. Sulfur cycling proves equally intricate. Sulfate-reducing bacteria use sulfate as an electron acceptor while oxidizing organic matter, producing hydrogen sulfide. Sulfide oxidizing bacteria reverse this process, oxidizing hydrogen sulfide back to sulfate. Intermediate oxidation states elemental sulfur, thiosulfate, sulfite provide additional metabolic opportunities for specialized bacteria. At hydrothermal vents, the dramatic sulfide gradients support dense bacterial populations exploiting this chemical energy source. In sediments away from vents, sulfur cycling proceeds at lower rates but remains significant. The deepest sediment layers contain bacteria that have been buried for thousands or millions of years. These subsurface bacteria exist in an extraordinarily slow metabolizing state, sometimes called cryptobiosis or near dormancy. Radiocarbon dating of organic matter in deep sediment cores indicates some bacterial cells may have been isolated from the surface world for over 10 million years. During this time, they have reproduced perhaps only a few times, if at all, maintaining minimum metabolism necessary to repair cellular damage without actually growing. The generation times time from one cell division to the next may exceed thousands of years, making these the slowest growing organisms known. These ancient bacteria face constant cellular damage from background radiation, chemical degradation of macromolecules, and spontaneous errors in DNA replication. Without repair mechanisms, accumulated damage would eventually kill the cells. The bacteria must maintain functional DNA repair enzymes, protein quality, control systems, and membrane maintenance machinery, despite metabolizing at barely detectable rates. How they accomplish this remains incompletely understood, but it demonstrates that life can persist in seemingly impossible conditions for geological timescales. Viral particles outnumber bacterial cells in trench sediments by roughly 10 to 1, similar to ratios observed throughout the ocean. These viruses infect bacteria, injecting genetic material and hijacking cellular machinery to produce new viral particles. When the infected bacterium ruptures, it releases viruses that can infect other cells. This viral predation constitutes a major mortality factor for bacteria, potentially killing 10 to 40% of the bacterial population daily in productive environments. In the slow-growing Hadal sediment communities, viral infection rates are lower but still significant, contributing to nutrient recycling by releasing cellular contents from dead bacteria. Some Hadal bacteria harbour their own genetic parasites, plasmids, and transposons that exist as extra DNA elements within cells. These mobile genetic elements encode genes that benefit their own replication without necessarily helping the host cell. Antibiotic resistance genes often spread via plasmids, allowing bacteria to share resistance even between distantly related species. In the Hadal zone, plasmids carry genes for pressure adaptation, metal resistance, and specialized metabolic capabilities. Horizontal gene transfer the movement of genes between organisms via plasmids, transduction by viruses, or direct DNA uptake allows rapid spread of adaptive traits through bacterial populations, accelerating evolution beyond what vertical inheritance alone would permit. The spatial distribution of microbial communities in trench sediments shows clear stratification. The top centimetre contains the highest cell densities, with bacteria exploiting fresh organic matter and dissolved oxygen from overlying seawater. Below this, oxygen depletes and anaerobic bacteria dominate. Nitrate-reducing bacteria occupy the next layer down. Sulfate reduction occurs. Deeper still, methanogenesis takes place in the deepest layers, where all other electron acceptors have been depleted. This vertical zonation reflects thermodynamic hierarchy organisms using the most energetically favourable metabolic pathways outcompete others for organic matter in the upper layers, while less favourable pathways become dominant only where preferred electron acceptors are unavailable. The total biomass of microorganisms in Hadal trenches, while low per unit volume compared to surface waters, remains substantial. When integrated over the trench's entire volume, estimates suggest the Mariana Trench contains approximately 10 billion metric tons of microbial biomass, rivaling the total biomass of all humans on Earth. This biomass turns over very slowly. Individual cells may live decades or longer, but collectively represents a significant reservoir of organic carbon and a major component of the Hadal ecosystem. Bioluminescence in the Hadal zone. At depths where sunlight has not penetrated for millions of years, life produces its own light. Bioluminescence, the generation of light through chemical reactions in living organisms, occurs throughout the ocean's depths, including the Hadal zone. Unlike the complex eyes and vibrant colours of surface organisms evolved to work with sunlight, deep-sea bioluminescence operates in complete darkness, serving functions entirely divorced from solar radiation. The light produced ranges from dim blue-green glows, barely visible to human eyes, to brilliant flashes that momentarily illuminate the surrounding water. The biochemistry of bioluminescence involves a light emitting, the molecule called luciferin reacting with oxygen in the presence of an enzyme called luciferase. The reaction produces a molecule in an electronically excited state which releases energy as a photon of light when returning to ground state. Different organisms use different luciferins and luciferases, indicating bioluminescence. Evolved independently multiple times. Marine organisms predominantly produce blue or blue-green light, wavelengths that travel farthest through seawater before being absorbed. Red light, common in terrestrial bioluminescence like fireflies, gets absorbed within feet in seawater, making it effectively invisible. At distance, the energy efficiency of bioluminescence exceeds 90% in some organisms, far superior to any human-made light source. Nearly all the chemical energy released in the luciferin luciferase reaction converts to light rather than heat. This efficiency matters critically in the deep sea, where food scarcity makes energy conservation essential. An organism wasting energy generating heat instead of light would be at a competitive disadvantage compared to one producing pure light with minimal energy expenditure. Deep-sea fish employ bioluminescence for multiple purposes. Counter-illumination, used by fish living in the twilight zone, where faint sunlight from above creates silhouettes, involves light organs on the fish's underside, matching the intensity and colour of downwelling light. This makes the fish invisible when viewed from below, eliminating the shadow that would otherwise reveal its presence to predators or prey. The fish must continuously adjust light output as it moves through different depths where light intensity varies. Some species harbour bioluminescent bacteria in specialised organs, while others produce light using their own biochemistry. Predatory fish use bioluminescent lures to attract prey. The anglerfish's dangling lure, extending from a modified dorsal fin spine, contains bioluminescent bacteria that glow continuously. The bacteria receive nutrients and oxygen from the fish's blood, vessels supplying the lure, while providing light that attracts curious prey close enough for the anglerfish to strike. The symbiotic bacteria belong to the genus Vibrio, capable of free-living existence, but achieving much higher densities inside. Light organs where the host provides ideal conditions. The bacteria communicate using chemical signals called autoinducers, only producing light when their population density exceeds a threshold, a phenomenon called quorum sensing that ensures light. Production occurs only when enough bacteria are present to generate visible glow. Dragonfish possess light organs beneath their eyes that function as searchlights. These fish can aim the light beam by moving their eyes, illuminating prey without alerting them. Most deep-sea organisms cannot see red light, so some dragonfish species produce red bioluminescence using unique biochemical pathways. This creates an asymmetric predator-prey relationship where the dragonfish can see prey illuminated by red light, while the prey remains unaware of being observed. The red bioluminescence requires a modified luciferin-luciferase system, different from the typical blue-green light production, representing a remarkable evolutionary innovation. Flashlight fish carry bioluminescent bacteria in large organs below their eyes. These fish can cover the light organs with dark tissue, effectively turning the lights on and off. Schools of flashlight fish coordinate their flashing, creating patterns that may confuse predators or facilitate communication in school. The bacteria continuously produce light, so the fish controls visibility by blocking or exposing the light organs. Rather than controlling bacterial light production directly, many deep-sea organisms use bioluminescent displays to startle or confuse predators. Certain squid eject bioluminescent mucus when threatened, creating a glowing cloud that distracts the predator. While the squid escapes in darkness, some deep-sea shrimp vomit bioluminescent fluid into the water when attacked temporarily, blinding the predator with brilliant light. The ostracod vagula, a small crustacean, releases bioluminescent chemicals that mix in seawater, creating a luminous cloud. These defensive bioluminescent displays often produce much brighter light than lures or counter-illumination, prioritizing intensity over energy, efficiency when survival is at stake. Communication between individuals of the same species may utilize bioluminescent signals. Certain deep-sea squid produce species-specific light patterns, possibly used for mate recognition or territorial displays. The patterns involve coordinated activation of multiple light organs distributed across the body, creating sequences visible to conspecifics. The neural control systems required to generate these patterns indicate sophisticated information processing, challenging assumptions about invertebrate cognitive capabilities. In the hadal zone specifically, bioluminescence becomes less common than in shallower deep-sea regions. The extreme scarcity of food makes the energy cost of maintaining bioluminescent organs potentially prohibitive. However, bioluminescent bacteria exist in trench sediments, producing faint glows when disturbed. Some hadal amphipods display bioluminescence, though whether they produce it themselves or acquire it from bacteria remains unclear. The Mariana snailfish likely encounters bioluminescent prey organisms, and its functional eyes suggest vision remains useful for detecting these brief light flashes in the otherwise absolute darkness. The quantum mechanics of bioluminescence production involves precise molecular geometry. The luciferin molecule must be positioned correctly relative to luciferase's active site for the reaction to proceed efficiently. The excited state molecule must have space to vibrate and rotate as it releases energy. Constrained molecules may release energy as heat rather than light, reducing efficiency. Evolution has optimized these molecular interactions, producing light generation systems that approach theoretical maximum efficiency. Some organisms acquire bioluminescent capability through diet. Rather than synthesizing components themselves, certain fish consume bioluminescent prey and sequester the functional luciferin in their own light organs, using it with their own luciferase enzymes. This dietary acquisition of bioluminescent compounds reduces metabolic costs compared to synthesizing luciferin de novo. The evolutionary transition from synthesis to dietary acquisition involves loss of biosynthetic pathway genes, a form of genomic streamlining that occurs when environmental conditions reliably provide needed compounds. The wavelength of bioluminescent light correlates with habitat depth in some taxa. Species living in the upper mesopelagic zone, where some sunlight penetrates, tend to produce light matching the residual sunlight's spectrum blue wavelengths around 470 nanometers. Deeper living species show more variation in bioluminescent wavelengths, ranging from 450 to 490 nanometers, because matching downwelling sunlight no longer matters when no sunlight reaches their habitat. The specific wavelength produced depends on the luciferin and luciferase structures, with subtle changes in molecular structure shifting emission wavelength. Pressure affects bioluminescence production by influencing reaction kinetics. The luciferin-luciferase reaction involves molecular collisions and conformational changes, potentially sensitive to pressure. Studies of bioluminescent bacteria cultured under pressure reveal that light production continues at hadal pressures, though reaction rates may change. The bacteria adjust light output by modulating luciferase expression levels rather than through direct pressure effects on individual enzyme molecules. The evolutionary origins of bioluminescence remain incompletely understood. The diversity of luciferin types suggests the capability evolved independently at least 50 times across different lineages. Some luciferins are modified amino acids. Others are modified nucleotides or lipids. This diversity indicates many evolutionary pathways can lead to bioluminescence, suggesting it's a relatively accessible adaptation that emerges whenever its benefits exceed its costs. In the deep sea, where visual predation pressure is intense and mate finding is difficult, bioluminescence's benefits apparently exceed costs for many species. The physics of extreme depth and water properties. Water at the bottom of the Mariana Trench behaves differently than surface water in ways that affect everything from sound, transmission to chemical reactions. While we think of water as incompressible, extreme pressure does compress it measurably. At Challenger Deep, water density increases by approximately 5% compared to surface water at the same temperature. This compression occurs because pressure forces water molecules slightly closer together, reducing the volume a given mass of water occupies. The density increase seems small but has significant effects on buoyancy, sound propagation, and the behavior of dissolved substances. The molecular structure of water consists of one oxygen atom bonded to two hydrogen atoms at an angle of 104.5 degrees. This asymmetric structure creates a polar molecule with partial positive charge on the hydrogen atoms and partial negative charge on the oxygen. Water molecules form hydrogen bonds with neighboring molecules, creating a loosely organized structure that breaks and reforms constantly. Pressure affects this hydrogen bonding network. At extreme pressure, water molecules pack more efficiently, potentially altering the average number of hydrogen bonds each molecule forms. Computer simulations of water under trench pressures suggest subtle shifts in hydrogen bonding, patterns that could affect how dissolved substances interact with water. The viscosity of water, its resistance to flow, increases with pressure and decreases with temperature. At trench depths where pressure is extreme but temperature near freezing, these effects partially counterbalance. The pressure increase would raise viscosity, making water thicker and more resistant to flow, but the cold temperature already maximizes viscosity at any given pressure. The net result is that trench water has viscosity approximately 30% higher than warm surface water. This increased viscosity affects how small particles settle, how dissolved molecules diffuse, and how organisms move through water. Swimming requires more energy at depth because the water resists movement more strongly. Sound propagation in seawater depends on water's density, compressibility, and temperature. Sound waves travel faster in denser, less compressible media. In the Mariana Trench, sound speed reaches approximately 5,400 feet per second, roughly 10% faster than in warm surface water. This increased sound speed affects marine mammal communication, sonar ranging, seismic wave transmission. The ocean contains a sound channel called the SOFAR channel at depths where sound speed reaches a minimum that traps sound waves and allows them to travel thousands of miles with minimal attenuation. The trench's depth places it well below the SOFAR channel, in a region where sound propagation follows different rules. Seismic waves from earthquakes propagate through both solid earth and ocean water. When an earthquake occurs along the subducting Pacific plate beneath the Mariana Trench, it generates seismic waves that radiate outward in all directions. Some waves travel through the plate itself as body waves, compressional P waves, and shear S waves that move through solid rock. Other waves travel along boundaries as surface waves. The water column overlying the earthquake focus transmits acoustic waves, but cannot transmit shear waves. Since fluids don't support shear stress, this creates characteristic patterns in seismograms recorded by ocean bottom seismometers, with P wave arrivals followed by waterborne acoustic phases but lacking the S wave arrivals recorded on land. The refractive index of water, the ratio of light speed in vacuum to light speed in water, changes with pressure. Light travels slower in water than in vacuum due to electromagnetic interactions between light and water molecules. At surface pressure, water's refractive index is approximately 1.33, meaning light travels 33% slower in water than in vacuum. At trench pressures, the higher density increases the refractive index slightly to about 1.36. This affects how light bends when entering water from other media, though at trench depths where no sunlight penetrates, the main relevance concerns bioluminescent light propagation. The higher refractive index at depth means light bends more sharply at interfaces, potentially affecting how bioluminescent displays appear to organisms viewing them. The dielectric constant of water, a measure of how well water molecules orient in response to electric fields, also changes with pressure. This property affects how ionic substances dissolve and how charged molecules interact. The dielectric constant decreases slightly at high pressure, potentially affecting protein folding and enzyme function by altering electrostatic interactions. Organisms adapted to trench pressures have proteins whose electrostatic interactions remain optimal under the modified dielectric conditions, representing another subtle adaptation to extreme depth. Radioactive decay of potassium-40, uranium and thorium in seawater produces heat, though the amount is minuscule. In the deep ocean basins, where water residence times exceed 1,000 years, radioactive heating becomes barely measurable. The trench water contains these naturally occurring radioactive isotopes at concentrations typical of seawater, contributing negligibly to the thermal environment, but providing a constant source of ionizing radiation. Organisms living in the trench receive continuous, low-level radiation exposure from dissolved isotopes and from cosmic ray particles that penetrate even to the ocean floor, though at greatly reduced intensity compared to the surface. The isotopic composition of oxygen and hydrogen in water varies slightly with depth due to fractionation processes. Evaporation at the ocean surface preferentially removes light isotopes, leaving surface water enriched in heavy isotopes. Precipitation returns. Light isotope-enriched water. Deep water formed in polar regions, where precipitation exceeds evaporation, has different isotopic composition than deep water formed in temperate regions. Analysis of oxygen and hydrogen isotopes in trench water reveals its origin in specific source regions, allowing oceanographers to trace water. Mass movements through the deep ocean. The Mariana Trench contains water that originated near Antarctica, travelling northward along the ocean floor over centuries before arriving at the trench. Noble gases, helium, neon, argon, dissolve in seawater in proportions determined by temperature and pressure at the ocean surface, where water last contacted the atmosphere. Once water sinks below the surface, gas exchange ceases and dissolved gas concentrations become fixed, except for radioactive production of helium from uranium and thorium decay. Measurements of noble gas ratios in deep water provide information about when and where that water was last at the surface. Trench water shows noble gas. Signatures indicating surface contact occurred decades to centuries ago, consistent with deep circulation timescales. Anomalously high helium concentrations indicate proximity to hydrothermal vents, where helium from Earth's mantle enters the ocean. Phase transitions of water under pressure create exotic ice forms that exist only at high pressure. At surface pressure, water freezes to ice E, the familiar hexagonal crystal structure. At higher pressures, different ice polymorphs become stable ice 2, ice 3, ice 5, ice V ice, each with distinct crystal structure and properties. However, the pressure at the Mariana Trench, though enormous by everyday standards, remains below the threshold for these exotic ice phases. At 1,086 atmospheres and temperatures above 34 degrees Fahrenheit, liquid water remains stable, creating exotic ice phases would require either much higher pressure, much lower temperature than occur in the trench. The critical point of water, the temperature and pressure above which liquid and gas phases become indistinguishable, lies at 705 degrees Fahrenheit and 3,200 atmospheres. Hydrothermal vent fluids approaching these conditions show unusual properties. Near critical and supercritical water dissolves organic compounds, readily acting as a powerful solvent very different from ordinary liquid water. Some of the hottest hydrothermal vents near the Mariana Trench may discharge fluid at conditions approaching water's critical point, creating unusual chemical environments where water's solvent properties differ dramatically from normal.